now we will start the last week of this course, and in this week I will talk a little bit more about band theory of solids, and we will particularly show how band theory of solids can be used to understand the different kinds of solids. Okay. In the last week we learnt about the origin of bands. We saw how we can understand why bands arise in a solid, and now we want to actually take that theory and apply it to see how bands affect the properties of solids. Okay. And first in the first lecture I will make some remarks about band theory of solids. Okay. This will be sort of summarizing, but also making some additional remarks about the band theory of solids, and I will talk about a quantity called crystal momentum. Okay. And this week 12 lecture 1 will be more about band theory and crystal momentum. Now, let me make some observations about band theory of solids. Okay. So, we have already seen how we got bands, and what I want to say is that a single band represents a relation E of k. Okay. And basically you have different bands, okay, given by E1 of k, E2 of k, etc. So, each particular band will have its relation E of k. Okay. And now this is a very interesting picture that we have. The pictorially what we have is something like this. You have k and you have E, okay, and for a band you have some relation between E and k, okay, some relation between E and k that represents the band. Now, so the allowed values of k are due to the von Karman boundary conditions, and so what we said was that if you are doing in one dimension, then k should be n pi by L, should be a multiple of n pi by L. If you are doing in higher dimensions, then k should be something like nx pi by Lx plus nx pi by Lxi plus ny pi by Ly j plus nz pi by Lz k. Okay. This is a von Karman boundary condition that says that the Lx, Ly and Lz is the size of the system, and usually Lx, Ly and Lz are very large. So, the allowed values of k are very closely spaced. Okay. And what you notice is that the allowed values of k are evenly spaced. So, if you look at the allowed values of k, if you look at this energy diagram, you have specific values of k, but you have a large number of them. So, we can draw a smooth curve, okay, which is an approximation, but it is a very good approximation for this band structure. Okay. So, the allowed values of k are actually very closely spaced, okay, and so that naturally gives us bands, it gives us smooth bands. Okay. And again they are closely spaced because Lx, Ly and Lz are very large. Now, the next point is actually very important. It is the fact that E of k is periodic with the periodicity of the reciprocal lattice, okay, and we assume energy E of k to be a smooth function, okay, and just these two restrictions, okay, if you have a periodic function that is smooth, okay, then basically it implies that there is a finite range for every band. So you can see this in the following way, that if you have this periodic function and let me put this as the period. Okay. So, if it starts here, then it has to, when it comes back to this point, it has to come to the same value. Now, in between it can do anything, okay, but what you see, since it has to come back to this point, okay, and it is a smooth function, okay, basically what this says is that there is a finite range of energies. So, you just have a finite range of values. Okay. So, this is the range of allowed values of the energy of this band. Okay. So, you see that natural consequence of the periodicity is that there is a finite range of energies for each band. Okay. The other natural consequence of the periodicity in reciprocal space is that your k can be restricted to the first Brillouin zone, okay, because this energy as a function of k will be periodic. Okay. So, it will be the same function over and over again. So, all you need to do is to look at the first Brillouin zone, okay, and in one dimensions this first Brillouin zone is minus pi by a to pi by a. In higher dimensions you have to look at the three dimensional object, that is the first Brillouin zone. And this is another point I want to make. We do not actually, if you want to exactly calculate the band structure, you need to do advanced quantum mechanical calculations. So, you need to really solve the Schrodinger equation. We actually never solved the Schrodinger equation, we just qualitatively described why bands should be there and what their structure is supposed to be. But if you really want to calculate it starting from first principles, you will have to do advanced quantum mechanical calculations. Okay. The other thing is that there is no restrictions on bands crossing each other except in some cases. Okay. In some cases, what I mean by some cases is that when you have bands, when you have two wave vectors that are related through each other through the reciprocal lattice, okay, then there is some non crossing conditions, but other than that bands can cross each other. And the last point is that in higher dimensions you require a path in reciprocal space. You cannot just show the band in terms of a simple scalar axis for k. For example, you had gamma to x to L to W and so on. Okay. So, you have some path in k in reciprocal space that is required to depict the band structure. Okay. So, this is only to depict, okay, only for depiction of the band structure on paper. Okay. You require this path in reciprocal space. Okay. Next, I will come to the concept of crystal momentum. Okay. Now, if you take a free electron, for a free electron without a lattice, this is no lattice. Okay. The wave function is given by some constant times e to the I k dot r, and if you calculate the momentum, okay, so to calculate the momentum you operate it by the momentum operator. And the momentum operator is minus I h cross times gradient. Okay. Now, gradient of this whole thing, okay, will just give the same function multiplied by I k. Okay. So, this will just give you minus I h cross times the gradient of a e to the I k dot r, and this gradient is just equal to I k times the same function. Okay. So, I can write this as I k into minus I h cross, that is just h cross k times psi of r. Okay. And so, you immediately you identify that this is the momentum. Okay. So, this is the eigenvalue of the momentum, and that is the value of the momentum in any experiment. You will see this value for momentum of free electron. Okay. Now, for what about block electrons? Okay. Now, we have psi of r given by e to the I k dot r multiplied by some periodic function. where UK has the periodicity of the Bravais lattice. KFR for any R contained in Bravais lattice, any R. So, you can take any lattice translation vector and you will get you will have this relation. Okay. So, now if you calculate P operated on psi of R, okay, now you will have minus I h cross and you will have the gradient operated on this product of functions, okay, and so you will get two terms, one involving the gradient of e to the I k dot r and the other involving the gradient of u k of r. The term involving the gradient of e to the I k of r will simply look like h cross k and you will have psi of r, but you will have another term that looks like this. It looks like minus I h cross e to the I k dot r times the gradient of u k of r. Okay. The point I am making is that this is not an eigenfunction of. So, psi of r is not an eigenfunction of momentum. However, we still see that if you look at this, there is at least one term that looks like an eigenvalue expression. So, you still have it looking like an eigenvalue expression, but there is an additional term. Okay. So, put a vector here, all the h cross k will be a vector. Okay. So, you identify h cross k is like a momentum, okay, and you call it the crystal momentum. Okay. And so, it is like this momentum of this electron that is in this whole crystal. Okay. It is not the true momentum, but it is momentum with the restriction that it experiences this periodic lattice. Okay. And there is a connection with the full momentum, okay, but we will not talk about it, okay, but this is called the crystal momentum, and so you can really think of k as in some ways related to the momentum. It is not a true momentum, but the term used is crystal momentum. Okay, in fact, you can do more advanced quantum mechanics to explore the connection between crystal momentum and real momentum, but that will not be covered in this course. The next important idea is the following, that the way we are describing the band theory, what we do is you first make the bands then fill electrons. Okay. And this is the picture that we will be using. Okay. So, for example, if you look at let's look at the one dimensional case, okay, that is easy to illustrate. Okay. So, what you do first is you calculate the entire band structure, and you just need to restrict to the first Brevon zone because of the periodicity. And now what you do is you start making the bands, okay, and let us say I will just give some examples of bands. Let us say you have something that looks like this. I am just showing a few bands. Okay. Now, how do you fill electrons into these bands? Okay. Now, so first thing you have to do is to calculate the number of electrons. Equal to number of atoms times valency. Okay. And in the bond 1 carbon boundary condition, we wrote the total number of atoms as Nx times Ny times Nz times the valency. I will just say V for valency. Okay. So, now you can see in 1D, in one dimension, this is just the, so in 1D number of electrons is equal to Nx times the valency, and Nx is just the length in the x direction divided by A times the valency. Okay. So, now let's see what this looks like. Okay. So, so basically you have this is the total number of electrons. Now, again we recall the allowed values of k is equal to n pi by Lx. And so if you go from number of, so if you ask how many k values are there from minus pi by a to plus pi by a. So, total number of k values between minus pi by a to plus pi by a. Okay. So you can do this in the following way. So, you see that this spacing, this from minus pi by a to plus pi by a, you have a range of 2 pi by a. Okay. And if you look at this number, the allowed values of k is n pi by Lx. So, the spacing between k values is pi by Lx. So, if you just divide this by pi by Lx, you will get the total number of allowed values of k. Okay. And this is equal to twice Lx by a. Okay. That means Lx by a. So, you take the, so you have this many values. So, this is equal to twice number of atoms. Okay. Lx by a is nothing but the number of atoms. Okay. So, basically in this range from 0 to pi by a, you have the number of, you have a total of nx states. Okay. Here you have nx states, and so on. Okay. And again for the other, you can show this for each of the bands, there are total of nx states. Okay, I am just showing some of the states here. Now, if you want to start filling electrons, now you have to fill nx into v electrons. Okay, so so what you will do is depending on your value of v, you will start filling from the lowest. So, you start filling from here, you start filling electrons starting from the lowest state. Okay, okay. Then you go to the next state. If you have more states, you fill the next one. And depending on how many ever you have, then you start filling from here. Once you get here, then you start filling this also. Okay, so you start filling this way, and then you keep going on till you exhaust all the electrons. Okay, this is a very central idea to the band theory of solids, that you start filling electrons from the lowest energy and fill them up. Okay, now this is the band structure. This is the electronic configuration at, this gives the electronic configuration at T equal to 0 Kelvin. That is, at T equal to 0 Kelvin, only the lowest energy configuration is allowed. At finite temperatures, you have some electrons that might be excited to higher bands. Okay, so at finite temperature, there could be excitations of some of these electrons to higher levels. Okay, so in that case, the electronic configuration is more complicated. So now you can ask what is the Fermi energy and what is the role of temperature. So as we saw in the last figure, okay, you can have these bands, and you can have so you can say at T equal to 0, okay, the highest occupied energy is called the Fermi energy. Okay. So, if you go back to what we saw, okay, then this would be the, in this case, this would be your Fermi energy, because I mean, we assume that all the, when you filled all the electrons, you reached up to this level. Okay. So, now obviously, if you have temperature, then you know, you have some excitation of electrons. Okay. And but the easiest way to define the Fermi energy is through T equal to 0. Okay. At finite temperature, you have excitation of electrons of some electrons to higher energies. So, now there are various cases that can happen, and we will look at this in more detail a little later. Okay. Now, it could happen that when you fill okay, I'm showing, I'm using 1D for illustration, but you can do this for arbitrary dimensions. Okay. Now, when you take these bands and you start filling them, okay, it could happen that your Fermi energy is right here. Okay, it could happen that your Fermi energy is right here. It could or it could happen that your Fermi energy is here. So, this is case 1, case 2. EF in case 2, EF in case 1. Okay. And in the first case you see that that you have some bands that are you have in this case you have some bands completely filled, others completely empty. And in this case you have some bands, one or more bands can be partially filled. Okay, so you have one or more bands. In this case I showed two bands that are partially filled. You could also have a case where only one band is partially filled. Okay. And this information about how the Fermi energy is related to the band structure. Okay, so this will turn out to be very crucial in describing the electronic properties of solids. Okay. So with this I will conclude this lecture for today. Okay. And here in this lecture we sort of summarize some of the points about band theory of solids, and we looked back, and we also looked at how to fill electrons into the bands. In the next lecture I will talk about the concept of density of states. Thank you.